In the early morning of December 7th, something changed. 3I Atlas, the interstellar object that had defied expectations at every turn, had just crossed Jupiter's orbital corridor. It should have stabilized. Instead, it began shedding mass at a rate that caught every major observatory off guard. From Chile to Hawaii, from the JWST to ground-based spectroscopy labs, the reports were identical. 3I Atlas was ejecting material. Fast. Too fast. This wasn't chaotic fragmentation. This was controlled shedding. Geometric, layered, timed. And the deeper scientists looked, the more the energy equations broke down. Because the mass loss didn't follow sunlight, didn't follow gravitational drag, didn't even match known comet behavior. It responded to Jupiter's influence, or to something hiding within its magnetic shadow. Let's begin. Something subtle, almost silent. A shift that would trigger confusion across multiple observatories. 3I Atlas had just entered the outer region of Jupiter's orbital corridor, trailing the gas giant's path through space by several million kilometers. This zone, far beyond the warm grasp of the inner solar system, is usually calm, cold, sparse. But as soon as 3I Atlas crossed into it, the object responded, violently yet methodically. What astronomers witnessed wasn't the beginning of disintegration. It was the beginning of activity. The object began to lose mass. At first, the signs were faint. A slight increase in infrared reflectivity. Then a sharpening of the coma's edge. Within an hour, ground-based telescopes from Hawaii to Namibia reported a measurable outflow of volatiles, particularly carbon monoxide, carbon dioxide, and trace hydroxyl signatures. This was strange. Objects don't sublimate that far from the Sun. The average solar flux at that distance, over 5 astronomical units, is less than 4% of what it is near Earth. Comets typically fall quiet in that region. But 3I Atlas was doing the opposite. The object was waking up again, but not because of heat. The leading hypothesis among early observers focused on gravitational shearing. Jupiter is massive, its presence warps local space. As 3I Atlas passed through the gas giant's trailing Lagrange region, some thought tidal interactions might have triggered internal stress. But none of the expected outcomes were visible. There were no chunks, no jets aligned with spin, no torque drift. The ejection was uniform, like a pressure release valve opening, not a structural rupture. Within 3 hours, multiple observatories confirmed the onset of dust. Not just gas emissions, but fine particles, micron scale, visible as a sudden bloom in the optical spectrum. When adjusted for albedo and angle, the readings showed a halo of light stretching more than 20,000 kilometers in radius. Yet the nucleus remained sharply defined, refusing to blur or tumble. That fact alone ruled out natural fragmentation. Then came the energy signature. An uptick in emissions was detected not in infrared, where thermal activity should peak, but in a narrow ultraviolet band. This is where the puzzle deepened. The wavelengths corresponded to ionized carbon and hydroxyl dissociation, reactions that require energy, yet were being recorded without any nearby heat source. The spectral ratios mimicked those of a comet near Mercury, not one floating past Jupiter. Scientists were stunned. Something was energizing the interior of this object, but it wasn't the Sun. The moment 3I Atlas crossed the boundary of Jupiter's gravitational corridor, it changed. It began ejecting material as if triggered, and not randomly, but in pulses, timed and proportionate. By the end of the initial 6-hour observation window, it had released more mass than during its entire approach to the Sun. Yet it showed no sign of spinning, wobbling, or falling apart. In fact, it seemed composed. A growing theory began to emerge behind closed doors. What if this wasn't natural mass loss? What if the object was reacting not to sunlight, but to gravitational vectoring, using its position relative to Jupiter to initiate some internal process? A few even speculated that the region's low-density plasma environment might be acting as a kind of relay, a signal, or even a trigger. These were fringe ideas, still are. But the data forced the questions. Something changed the moment 3I Atlas crossed Jupiter's path, and that change didn't follow the rules, because here, in the cold outer dark, far from the Sun's influence, something woke up, and it began to let go. There's a rule in cometary science that almost never breaks. No heat, no activity. Volatile materials, like water ice, carbon dioxide, carbon monoxide, only sublimate when exposed to energy. Usually that energy comes from the sun. The closer a comet gets to the solar furnace, the more it boils off its icy reserves. This is what forms the iconic glowing coma and tail. But when 3I Atlas passed Jupiter's orbital zone on December 7th, something happened that shredded that rule. It began to lose mass, rapidly, and in a region of space where heat cannot explain it. At over 5 astronomical units away, solar radiation is too weak to drive significant sublimation. Temperatures at that distance average less than minus 100 degrees Celsius. Ice should remain frozen. Gases should stay trapped. If anything, 3I Atlas should have been entering a dormant phase. Instead, it did the opposite, ramping up to a mass ejection event that looked more like a near-solar outburst than a cold transit. The first clue came from the ultraviolet spectrum. Telescopes across Europe and South America began detecting elevated levels of hydroxyl radicals. A byproduct of water molecules breaking apart under UV light. Normally, this means water ice is actively sublimating. But the intensity of the signature didn't match the ambient UV flux in the region. In short, there wasn't enough sunlight to cause that much outgassing. And yet, it was happening. This was the first time scientists began asking a question they usually avoid. What if heat isn't the trigger? Instead of a surface warmed by the sun, maybe something internal had activated. Maybe energy was coming from within. But if so, how? Interstellar objects are not expected to carry internal heat. They've been drifting through space for tens of millions of years, frozen solid. Any radioactive decay would have long since faded. Any internal pressure would have equalized. So what was left? One theory pointed to latent phase transitions. Chemical compounds buried deep within the core that remain stable until disturbed by gravitational forces or structural strain. In other words, something inside 3I Atlas got nudged just enough, maybe by Jupiter's magnetic field or gravity well, to unlock stored energy. But even that couldn't explain the scale of the mass loss. By the end of the event window, researchers estimated that over 3 billion tons of material had been shed, without heating, without visible fragmentation, and without breaking the object's smooth rotational profile. The object was venting like an engine, not crumbling like a comet. Then came the infrared surprise. Infrared imaging from the James Webb Space Telescope revealed a shocking absence of thermal signature. Not only was the object not warming, it appeared to be cooling as it lost mass. This ran counter to every known sublimation process. Usually when an object vents gas, it loses heat, yes, but the act of sublimation itself radiates detectable energy. Yet 3I Atlas showed nothing, a thermal void. Like a system expelling gas while actively shedding its own heat at the same time. This created a strange analogy. Some researchers began describing it like this. Imagine a balloon deflating in deep space, not from external heat, but from a decision to release pressure, like the release was part of a function, not a failure. It was a deeply unsettling idea, because in space nothing chooses to do anything, unless it was designed to. No one's making official claims of artificiality. Not yet. But the mass loss without heat shattered too many expectations. We are witnessing something that mimics cometary physics, but doesn't obey it. And in that silent divergence, science begins to run out of language. As observers continued tracking 3I Atlas beyond Jupiter's orbit on December 7th, a new signal emerged, this time not in the ultraviolet, but in the visible light spectrum. At first, it appeared as a soft brightening. Then, the numbers shifted too far, too fast. Within a 6-hour window, telescopes around the globe reported a dramatic increase in reflected light from the object's surrounding coma. The readings were clear. 3I Atlas had just ejected a staggering volume of fine dust. But there was a problem, a big one. There was no disruption, no impact, no tumbling, no spin increase, no heat. And yet, the coma expanded. Not like a chaotic explosion, but like a shell unfolding in every direction evenly. That's not how dust behaves when released from a cometary body. Under normal conditions, comet dust is messy. Solar heat causes ices to sublimate and carry embedded dust outward. The grains vary in size and their distribution follows chaotic paths, some scattering, some lagging, many pulled into tail structures by radiation pressure. But the dust from 3I Atlas didn't scatter. It formed a spherical, uniform cloud around the object, expanding in concentric waves. The symmetry was too clean to be random. The brightness curve, when plotted, showed a steep vertical climb, then a flattening plateau, as if the dust reached a preset volume and held there. This type of light curve is unusual for mass shedding. In standard comet behaviour, a dust spike is often followed by continued brightening or chaotic fading. But not here. The cloud stabilised, not just optically, but structurally. Then came another oddity. The spectrum of the reflected light revealed something unexpected. The grains were small, consistent in size, and chemically homogeneous. Observatories analysing the scattered light from the coma found a high concentration of carbon-rich particles with low reflectivity, similar to aerogel materials or finely processed soot. No variation in grain structure, no silicates, no metals. This composition profile was almost engineered, and that word, engineered, began to show up in internal observatory notes, if not in the official reports. The big question was simple. How did so much dust get released so fast without a mechanical rupture? To produce a dust envelope of that scale through sublimation alone, a natural object would need to undergo violent thermal fracturing or internal pressurization. But again, this event occurred in deep cold. Infrared instruments recorded no surface heat spike. Structural imaging showed no cracking, no fragmentation trails, no deviation in the object's path or rotation. The dust came out, but the object stayed intact. A few teams proposed layered sublimation as an explanation, the idea that internal cavities filled with trapped dust and gas suddenly vented through surface fissures. But that model requires chaotic venting and irregular tail development. Instead, 3I Atlas's dust shell expanded uniformly, like a bubble inflating around the nucleus, consistent in all directions. Others theorize that the dust wasn't carried by gas at all, but released electrostatically. If the object had built up a charge while interacting with Jupiter's magnetic field, it's possible that particles near the surface were repelled all at once. Electrostatic lofting is known on small airless bodies like asteroids, but not at this scale, and certainly not with this symmetry. There was one more chilling detail. The outer edge of the dust envelope, the part furthest from the nucleus, pulsed. Subtly. At near regular intervals, photometric sensors detected a microvariation in reflectivity, like a thin wavefront travelling outward. The effect was faint but real, and no one has yet explained what could cause it. Natural mass shedding shouldn't look like this. Dust doesn't self-regulate, it doesn't pulse, it doesn't organise, and it definitely doesn't stop all at once in perfect spherical formation. Yet 3I Atlas did exactly that, and the dust still hangs in space behind it, like a marker or a trail. In the moments following the sudden mass ejection from 3I Atlas, scientists across multiple observatories began noticing something far more elusive than dust or gas. Something invisible, yet measurable, pressure. But not from within the object, from the surrounding space itself. On December 7th, several heliophysics instruments, including those aboard ESA's Solar Orbiter and NASA's Parker Solar Probe, detected faint but clear anomalies in the solar wind, localized shifts in plasma density and flow direction, right as 3I Atlas crossed a particular sector of Jupiter's trailing wake. These readings were small, subtle distortions in a sea of natural fluctuation, but they weren't random. The pattern appeared aligned with the object's trajectory, suggesting a kind of interaction between the interstellar visitor and the plasma environment around it. Solar wind is typically smooth and directional, shaped by the sun's magnetic output and deflected by planetary fields. At the distance of Jupiter, the stream should be diffuse, gentle, and mostly predictable. But in this case, as 3I Atlas passed through, that stream buckled, briefly, and then corrected itself. The distortion wasn't chaotic, it was shaped like a ripple, a compressed zone of plasma in front of the object, a weakened wake behind it, as if 3I Atlas was not being pushed, but was pushing back. This pattern was first flagged by instruments on board the Solar Terrestrial Relations Observatory, Stereo-A, which recorded a localized spike in ion density trailing the object by roughly 5,000 kilometers. That spike was consistent with a bow shock, a curved pressure front created when a solid object moves rapidly through a fluid medium. But 3i Atlas isn't solid in the traditional sense, and the medium isn't air. It's charged particles moving at hundreds of kilometers per second. And yet the bow shape held. This raised a provocative possibility. What if 3i Atlas isn't just passively moving through space, but interacting with it? Actively, dynamically. The idea suggests that the object either has a magnetic field of its own, enough to repel plasma and form a miniature magnetosphere, or is inducing one as it moves. Neither explanation fits a standard comet. No natural icy body has ever demonstrated that kind of electromagnetic footprint. Some scientists propose the object could be wrapped in an electrically charged shell, like the ionized envelope observed in some high-velocity meteors, but again this doesn't align with the scale, symmetry, or duration of the effect. The ripple followed 3i Atlas for nearly 40 minutes, maintaining its shape across multiple instruments. It wasn't a brief collision, it was a sustained interaction. Then came another layer of confusion. As the object moved forward, several observatories began detecting a mild reduction in cosmic ray flux in the region, immediately surrounding it. Cosmic rays are high-energy particles from outside our solar system. They're typically unaffected by small-scale magnetic fields, but around 3i Atlas, their density appeared to dip, ever so slightly, as if something was absorbing or redirecting them. The data points are still under review, but if confirmed, this would suggest not only an active pressure front in front of the object, but a shielding zone, like a barrier or a field. This kind of response is not consistent with any known natural mechanism. Comets do not create bow shocks in the solar wind, not unless they're actively venting near the sun, and even then, the shapes are messy. Here, the geometry was precise. The compression arc led the object like the prow of a ship cutting through water. Except space has no water, and nothing was supposed to be pushing back, yet something did. And now, for the first time, the environment around 3i Atlas may be revealing more than the object itself. In the hours following 3i Atlas's sudden interaction with Jupiter's orbital corridor, a disturbing silence began to register, not in sound, but in heat. As more observatories tuned their instruments toward the object, one question rose above the rest. Where was the warmth? Telescopes equipped with infrared detectors, including instruments aboard the James Webb Space Telescope, the Very Large Telescope in Chile, and the Spitzer Heritage Archive, all reported the same baffling absence. There was no thermal emission from the core, no heat signature, not even residual warmth from the recent mass ejection. It was as if 3i Atlas had entered a state of thermal suppression. To understand the magnitude of this anomaly, we need to revisit basic cometry physics. When an object in space vents material, whether it's from sublimation, internal pressure, or fracturing, the process typically generates heat. Energy is released when ices transition from solid to gas. Kinetic friction from particles escaping at velocity creates turbulence, and even passive radiation from sunlight warms the surface enough to produce a glow in the infrared spectrum. But 3i Atlas showed none of this. After venting billions of tons of gas and dust, its thermal profile dropped, not rose. This wasn't just counterintuitive. It violated one of the most fundamental expectations of celestial thermodynamics, that motion and mass, loss, equal heat. The first observers assumed calibration error. Telescopes were checked, filters recalibrated, atmospheric distortion corrected. But no fault could be found. The instruments were functioning perfectly. They just weren't picking anything up. By comparison, typical comets, even small ones, glow like embers in the cold vacuum of space when active. Their nuclei can reach temperatures above 150 Kelvin. The surrounding coma often radiates even hotter. But the surface of 3i Atlas was reading below 70 Kelvin. That's nearly the background temperature of space itself. In effect, the object wasn't emitting any measurable heat. It was absorbing it, or dispersing it so quickly that no residual trace could be found. This gave rise to a chilling idea. What if the object was not just cooling, but regulating its own temperature? One team from the Max Planck Institute proposed a layered shielding hypothesis. According to their model, if the surface of 3i Atlas is composed of carbon-rich compounds, perhaps aerogel-like materials or advanced lattice structures, it could theoretically radiate absorbed energy extremely efficiently, distributing heat evenly across its body and releasing it without building up a hotspot. That would explain the flat infrared curve, but it wouldn't explain why an object would evolve, or be built, to function this way. Another theory suggested the presence of internal heat sinks. If 3I Atlas contains a porous or hollow interior, any sudden energy from internal chemical reactions or tidal activation might be quickly drawn inward, dissipated across internal cavities, like coolant channels in industrial machinery. No comet has ever displayed this type of thermal silence after an outburst. None. The last time something even remotely similar was observed was during the flyby of interstellar object Oumuamua in 2017, which also showed no thermal glow despite its acceleration. But 3I Atlas's silence is more profound, longer, sharper. It's like a thermal void wrapped in a reflective shell. What makes this more unnerving is the timing. The thermal suppression occurred directly after the dust and mass ejection. In most scenarios, this is when thermal output peaks, but instead of glowing, the object dimmed, not in visible light, but in energy. It's as if 3I Atlas doesn't just move differently, it cools on purpose, and in the vacuum of space, cold is not absence. Sometimes it's control. As 3I Atlas continued shedding mass without spinning, fragmenting or heating, a strange new possibility began to circulate among planetary scientists. Maybe it wasn't solid at all, not in the way comets usually are. What if, buried beneath the thin reflective shell and symmetric ejection events, was something that space has never offered us before, an object with a hollow core? The idea didn't begin as speculation, it began with math. After the December 7th dust shell release, observatories attempted to estimate how much mass had actually been lost. By measuring coma brightness, particle density, and tail velocity, researchers calculated that billions of tons of gas and fine particulate matter had escaped into space. But when they ran the numbers backwards, trying to determine how much mass should have remained inside the object based on previous estimates of its size, the math broke. The object wasn't heavy enough. If the outer shell was doing the ejecting, the core should have collapsed under its own internal pressure. But it didn't. It stayed rigid. It kept its structure. Its path didn't shift. Its rotation didn't change. That left only one option. The mass wasn't coming from a dense interior, but from surrounding pockets, cavities within the object, possibly arranged in layers, like a compressed honeycomb or internal tank system. This is when the hollow core hypothesis was born. One team at the University of Arizona ran 3D density models based on observed acceleration, mass loss rate, and spin inertia. The most accurate simulation, the only one that didn't require the laws of physics to stretch, depicted 3I Atlas as a low-density shell with internal voids containing volatile-rich material. Think of it like a fragile eggshell filled with compressed gas chambers. Only in this case the shell never cracked. That's the problem. Comets that are porous or low density almost always fragment when they vent. They tumble, they lose symmetry. But 3I Atlas was ejecting from deep within and showed none of that. No destabilization, no distortion of trajectory. It was shedding from beneath a surface that stayed perfectly intact, as if the material was being routed outward through embedded channels. Naturally, this raised questions of formation. How could something with a hollow interior, potentially riddled with caverns or segmented chambers, survive interstellar travel? After all, this object has likely spent millions of years between stars, battered by cosmic rays, micrometeoroids, and magnetic storms. A hollow body should have fractured long ago. Unless, of course, the internal geometry gave it strength. Certain types of engineered materials, like carbon foams or metallic lattice structures, can remain light but resilient, strong enough to survive impact, pressure, and erosion. And while no one is ready to call 3I Atlas a structure, more scientists are beginning to admit that its behavior aligns more closely with engineered density profiles than with the chaotic mineral aggregates we typically see in natural bodies. The final piece of the hollow core puzzle came from radar. A series of passive radar measurements by the Goldstone Deep Space Network attempted to bounce signals off 3I Atlas's core during the dust ejection phase. What they received back was weak, too weak. The radar echo didn't match the expected profile of a solid nucleus. It was dull, as if the signal had passed through layers of a low-density material before reflecting back. This same attenuation is what radar signatures look like when aimed at empty caves inside asteroids. But 3I Atlas isn't an asteroid, and if it's hollow, if it's venting through an internal system rather than external cracking, then we may be dealing with an object whose purpose isn't just to fly through space. It might be designed to carry something, or worse, to leave something behind. One of the most unnerving aspects of 3I Atlas's journey through our solar system isn't its speed. It isn't the dust. It isn't even the silence in infrared. It's the symmetry. From the earliest observations, astronomers noted that this object behaved with an almost unnatural balance. Its coma, the glowing envelope of gas and dust surrounding its core, expanded evenly in all directions. Its jets, instead of firing chaotically from random locations as is typical in natural outgassing, appeared to pulse in patterns, and most importantly its motion remained perfectly stable, even as it vented massive amounts of material. That should be impossible. In natural comets, outgassing is messy. Solar radiation heats one side, the ice sublimates unevenly, and gas jets shoot from wherever the surface fractures. This introduces torque, a rotational force, that causes the object to spin. Over time, the comet begins to tumble. We've seen it time and time again with objects like Comet 67P Churyumov-Gerasimenko, which spun unpredictably as it neared the Sun. It's not just expected, it's inevitable. But 3I Atlas didn't tumble. After each mass ejection, its axial rotation remained locked, its orientation unchanged. It was as if the jets weren't reacting to heat or internal pressure, but were instead firing in perfect balance, cancelling out their own force, like a system designed to vent without destabilizing itself. This baffling symmetry extended beyond motion. Telescopes tracking the evolution of its coma brightness over time noticed a near-identical light curve before and after major events, as if the object was cycling through a repeatable pattern. The dust shell that expanded on December 7th showed an even distribution around the nucleus. No hotspots, no directional bias. And each vented pulse followed the last with near-perfect spacing. Some researchers described the pattern as machine-like, quietly of course, because publicly the term was dismissed. Still, the language in internal observatory logs became more curious. Precision venting, uniform polar ejection, symmetric jet signatures. These aren't terms you use for icy debris floating through space. These are terms associated with control. The James Webb Space Telescope, using its advanced NIRCam instruments, detected something else. During a multi-hour observation window, it captured a faint flickering pattern along the trailing edge of the object's coma. When the data was processed, this flickering revealed a pulse, a drop in brightness every 43 minutes, repeated 3 times. Exactly. Each drop lasted for 12 seconds. At first, teams assumed this was observational error, perhaps a glitch in image stacking or a shift in the telescope's orientation. But the same pattern was independently observed by a spectrograph in South Korea, and again by a ground-based observatory in Australia. The alignment of these observations, across hemispheres and systems, ruled out coincidence. The flicker wasn't a shadow, it wasn't a tail wobble, it was a timed event. That's when a new theory emerged. 3I Atlas might be symmetrical because it needs to be. If the object is using ejected mass for propulsion or stabilization, then firing in balanced intervals would allow it to correct trajectory, conserve spin, and maintain heading. Natural comets don't do this. They spin up and break apart, but 3I Atlas stays still, stays cold, stays clean. In spacecraft engineering, we use RCS, reaction control systems, to manage orientation without rotation. These systems fire short bursts of propellant in opposite pairs to adjust a vehicle's attitude without spinning it off course. It's a tactic, a design. And now 3I Atlas appears to be doing something eerily similar. In deep space, far beyond the sun's warmth, an object this symmetrical isn't following physics, it's following instructions. Since its first recorded pass near the sun, 3I Atlas has carried with it an optical mystery, a strange secondary feature stretching sunward instead of trailing away like a typical comet tail. This sun-facing appendage, dubbed the anti-tail, defied physics from the start. In standard cometary dynamics, dust and gas are expelled outward by solar radiation and swept back into the classic curved tail formation. The tail always points away from the sun, regardless of the object's direction of motion, because it's shaped by solar wind. An anti-tail, by contrast, is rare, and usually an illusion. Often it's caused by previously released dust lying in the plane of the object's orbit, reflecting light in such a way that it appears to form a backward tail, when in reality it's trailing debris catching a particular angle of illumination. But with 3I Atlas, the antitail was not a brief artifact of geometry. It persisted. From perihelion all the way past Mars and into the Jovian corridor, this strange sunward-pointing feature held its shape, visible across telescopes worldwide. Even more perplexing, it exhibited a narrow structure and consistent brightness, behaving less like a cloud of drifting dust and more like a coherent stream of particles. And now, on December 7th, after the object entered Jupiter's magnetic wake and released a fresh wave of mass, the antitail began to dissolve. Not gradually, not randomly, it fractured in layers. Observatories in Hawaii, Chile, and South Africa recorded the same moment. The antitail, once sharp and directional, began to blur. Then, distinct bands within it began separating, not dispersing like dust pushed by radiation pressure, but fragmenting along invisible seams. Within 4 hours, the once continuous beam had splintered into multiple ribbons, each vibrating slightly with phase-lagged motion, as if something unseen was disturbing its cohesion. What makes this even more puzzling is what didn't happen. Normally, when a tail dissolves, its material spreads outward and fades under solar wind drag, but this antitail didn't fade, it simply unraveled, like tension releasing from a coiled wire. Each strand drifted slowly, not with the forceful push of solar wind, but with gentle divergence, like they had been held together by something, and that something just let go. That brought attention back to the role of magnetism. Jupiter's magnetosphere is immense, the largest planetary magnetic field in the solar system, extending over 7 million kilometers. As 3I Atlas entered the edge of this field, data from ESA's solar orbiter showed a measurable electromagnetic shift in the surrounding plasma. A faint induction current was recorded just seconds before the antitail began its disassembly. This has led some scientists to suspect that the tail wasn't just dust, but ionized particles bound by electromagnetic alignment. In simpler terms, it might have been held together by a magnetic field of its own. If true, this would imply a level of active structure, a system, natural or artificial, capable of maintaining charged particle organization across hundreds of thousands of kilometers. That's not something any known comet has ever done, and it raises a darker possibility. What if the antitail wasn't a byproduct, but a function? One team from the Lunar and Planetary Laboratory at the University of Arizona proposed a conceptual model that the antitail was part of a propulsion or stabilization system, not just ejected material, but a controlled discharge aligned with the sun to regulate motion. In this model, the antitail acts like an exhaust channel, and when Jupiter's magnetic field interfered, the channel destabilized. The timing was too precise, the structure too elegant. Natural dust doesn't fracture in stripes. It doesn't hold in place for months and then disappear in coordinated phases. Yet that's exactly what this antitail did. And now that it's gone, one question looms. Was it ever supposed to be seen? In the aftermath of 3I Atlas's mass ejection and the unravelling of its mysterious antitail, another anomaly quietly appeared, not visible to the eye, but audible in the data. It was a shift, subtle, measurable, repeating, and it came from the Doppler signal. On December 7th at precisely 03:26 UTC, the Max Planck Radio Observatory in Germany registered a drift in the radio echo pattern bouncing off 3I Atlas. The change wasn't large, just a fractional deviation in the return frequency, but it persisted. Within 2 hours, the Very Large Array, VLA, in New Mexico, independently confirmed the same drift. By mid-morning, the anomaly had a name: Doppler drift. Doppler shifts are one of astronomy's most trusted tools. When a moving object emits or reflects a signal, the frequency of that signal changes depending on the object's velocity relative to the observer. If it's moving toward us, the signal compresses. If it's moving away, the signal stretches. By analysing this shift, astronomers can calculate an object's speed with incredible precision. That's why this anomaly was so strange. 3I Atlas had already been carefully tracked for months. Its velocity was stable, its trajectory, although slightly altered after perihelion, was predictable. But now, without warning, its signal was showing a slow, steady deviation. At first, some suggested it might be caused by interference, perhaps localized ionospheric distortion or calibration error. But when the Indian Deep Space Network, the Parkes Observatory in Australia, and a network of amateur radio astronomers across the globe began reporting the exact same shift, with identical frequency deltas, that explanation collapsed. The object had changed speed, slightly but consistently. It wasn't a random twitch. The Doppler drift followed a smooth curve, increasing over several hours, plateauing, then fading. The signal indicated that 3I Atlas had accelerated, not from gravitational influence, not from slingshot mechanics, but from something else. The direction of the acceleration was the most telling part, directly away from the Sun. That's not how physics works for inert space debris. Solar radiation can cause slight pressure effects, yes. So can asymmetric venting of gases from a comet's surface. But for this object to show measurable outbound acceleration, especially after mass shedding and tail dissipation, was contrary to every model. More importantly, the shift lined up perfectly with another event. The peak of the Doppler drift occurred minutes after the anti-tail dissolved. This temporal alignment is too close to ignore. One event released the object's forward-facing mass, the other, a measurable increase in speed away from the solar center. When modelled together, the correlation suggested a scenario straight out of spacecraft physics, momentum transfer. Essentially, 3I Atlas may have used the final ejection of its anti-tail material to gain velocity, not by accident but through directional thrust. If true, this means the object is steering. Astrophysicists at the University of Tokyo began testing orbital simulations using the Doppler-derived acceleration vector. When they recalculated 3I Atlas's trajectory using this small but meaningful thrust, the revised arc showed a deeper outbound escape, missing Earth's projected flyby window by several thousand kilometers more than expected. Not catastrophic, not dangerous, but deliberate. Comets don't do this. They tumble, they eject gas, but they do not accelerate in smooth solar-opposing vectors right after shedding mass. They don't maintain rotation during directional thrust, and they don't send Doppler signals that read like propulsion curves. But 3I Atlas just did, and now, with every tick of the shift, it's telling us something, not loudly, not visibly, but through physics. It's pushing away from us, from the Sun, from gravity, and perhaps toward whatever sent it. By December 7th, 3I Atlas had shed an enormous volume of material. Dust, gas, and vaporized particles streamed across hundreds of thousands of kilometers, and yet there was something missing. No fragments, no shattering, no signs of breakup. For planetary scientists trained on comets and asteroids, this absence was one of the most alarming signals yet. Because in the natural world, when an object releases mass at the speed and scale observed in Atlas, it typically leaves behind pieces. The physics demands it. Structural weakness causes internal stress, and when pressure builds up faster than the material can vent, things crack, they rupture, they splinter into debris fields. But 3I Atlas remained completely intact. Even under high-resolution imaging from deep space observatories, including adaptive optics from ground-based giants like Keck and VLT, no secondary bodies were detected trailing the object. No shards, no dust clumps with divergent trajectories, no fragments in the classical sense of cometary evolution. The object wasn't crumbling, it was functioning. Some scientists suggested that perhaps the fragments were just too small to be detected, that the ejected material had vaporized into fine particulates or sublimated before separation. But even this didn't hold up. Instruments monitoring polarization signatures, which can detect differences in particle size and reflective behavior, showed a remarkably clean and uniform composition in the expanding cloud. No hard chunks, no variation. Just fine, micron-scale dust and ionized gas, distributed evenly. And yet, despite the mass loss, the core remained visible, stable, bright. That's not how nature usually operates. Compare it to Comet Lenin or Shoemaker-Levy 9, both famous for their fragmentation events. When they shed mass under pressure or tidal forces, their nuclei broke into multiple distinguishable bodies. These fragments each left their own trail, followed their own orbital paths, and introduced rotational instability into the system. In the case of Lenin, the comet simply disintegrated under its own weak gravity. It left a smear in the sky. 3i Atlas left precision. The lack of fragmentation signatures raised a troubling question. If mass was being lost at this rate, but no solid bodies were breaking off, where exactly was the mass coming from? That's when a new concept began circulating in the closed circles of space modelling forums: volumetric shedding. Instead of fragments cracking off a brittle surface, volumetric shedding proposes that the object is ejecting internal material in a controlled, even manner, more akin to a balloon releasing gas through a valve than a rock shattering into pieces. This would explain why no rotation changes were detected, why no fragments drifted free, and why the density, brightness, and reflectivity of the remaining body stayed constant. This concept is radically foreign to traditional comet theory, but it's not foreign to engineering. In spacecraft design, there are systems that allow for precision mass ejection, whether for attitude control, thermal regulation, or propulsion. These systems are designed to maintain structural integrity while dispersing internal contents. The parallels are hard to ignore. Supporting this idea were observations from the Infrared Telescope Facility, IRTF, on Mauna Kea, which detected narrowband emissions within the coma during the mass loss event, signals that implied gas was emerging at consistent velocity from distinct, repeatable sites, not from a cracked hull, from fixed channels. In simpler terms, the object wasn't falling apart, it was venting on purpose, and because it wasn't breaking, that means it was holding itself together through internal reinforcement, symmetry, or perhaps intention. When a comet sheds mass but does not fragment, does not rotate, and does not deviate from its heading, it's no longer behaving like an inert body. It's behaving like a vessel, and whatever it's releasing may not be random debris, it may be something it carried, something it no longer needs, now released as part of a process we still don't understand. For nearly 2 weeks leading up to December 7th, 3 Atlas had gone silent in the radio spectrum. It wasn't just faint, it was absent, a complete blackout. Most active comets, when venting material, produce weak but detectable radio emissions. These can come from charged particles interacting with solar wind, from ionized molecules like hydroxyl radicals, or even from friction-based plasma effects inside the tail. And after 3i Atlas's perihelion burn, it had been giving off a complex set of irregular bursts, odd, layered emissions that didn't follow any clear modulation pattern, but were still there. Then it crossed into Jupiter's outer magnetic boundary, and everything went dark. No signal, no carrier, no background noise. The object's spectral signature simply vanished from radio instruments around the world. At first, researchers assumed interference. Solar storms had recently stirred up the heliospheric current sheet, and strong coronal mass ejections had caused localized blackouts across several observatories. But once conditions cleared and normal signal detection resumed across other known objects, 3i Atlas remained absent. It was like someone had shut off a transmitter. Then, at 4:52 UTC on December 7, just hours after the object's anti-tail collapsed and its Doppler drift began, the radio silence broke. Not gradually, instantly. The Deep Space Network station in Madrid picked it up first, a dense, low-frequency burst, concentrated in the L-band spectrum lasting nearly 9 seconds. The signal wasn't steady. It trembled, like a layered hum distorted by something rotational, but it had structure. Then it repeated. Roughly 30 minutes later, a second burst followed, nearly identical in duration and spectral weight. By midday, other stations across Japan, South Africa and Australia began logging matching events. 3 total emissions, all within a span of 90 minutes, all from the direction of 3i Atlas, all sharing the same harmonic footprint. This wasn't passive scattering, it was active emission. That distinction matters. In natural cometary behavior, radio signals are caused by interaction. Gas hits sunlight, ions move, electrons snap free, and plasma creates weak fields that give off radio noise. But these signals usually drift in frequency and fade quickly. What astronomers saw here was focused, repeatable, and narrow band, more like a radar return than a comet pulse. The pattern was too tight, too controlled. Spectral analysis performed by the Max Planck Institute for Radio Astronomy revealed sideband fluctuations in the signal that suggested internal oscillation. In other words, something inside the object might be modulating the frequency, almost like a rotating antenna. This led some to propose the existence of an internal cavity or rotating mass. And then came the strangest part. The third burst ended not with a fade, but with a cut, as if the source was shut off. Astronomers monitoring the tail region at the time noticed nothing unusual, no flare, no outgassing, no collision, just a signal that stopped with precision. Suddenly, the theory of internal components no longer sounded absurd. Was this a damaged signal, a distress pulse, a recalibration echo, or was it something simpler, a transmission? Several deep learning models were deployed to analyze the waveform. None of them returned any signs of modulation in a traditional sense. No language, no binary, no detectable data stream. But the consistent repetition, frequency targeting, and cutoff behavior led some engineers to suggest a comparison to beacon systems. In spacecraft design, beacons are simple, low-power radio pulses used for location tracking and orientation. They are basic, repetitive, and often activated during high-mass maneuvers or unexpected system changes. And here, right after Atlas shed a large portion of mass, shifted trajectory, and lost its anti-tail, a beacon-like burst reappeared. This wasn't background noise. It was the return of a voice. And if 3i Atlas was silent before, maybe it was simply waiting until now, until it had done what it needed to do, to speak again. As 3i Atlas continued on its outbound journey past Jupiter, scientists began noticing something increasingly peculiar, not in its brightness, not in its tail, but in its magnetic environment. Jupiter's magnetosphere is the largest and most powerful planetary magnetic field in the solar system. It stretches millions of kilometers outward, forming a giant magnetic bubble that traps charged particles and warps the solar wind. Any object passing near its boundary doesn't just coast through space, it interacts. And on December 7th, 3i Atlas didn't simply pass through Jupiter's field, it responded to it. Shortly after the reappearance of the radio bursts, deep space observatories began recording erratic disturbances in the local magnetic field near the object's location. These weren't coming from Jupiter itself, they were centered directly on the path of Atlas. The European Space Agency's JUICE probe, still on its early approach trajectory toward Jupiter, recorded a brief, localized spike in magnetic flux, one that aligned perfectly with the moment Atlas crossed a region known as the plasma sheet flank. This flank is a turbulent zone where Jupiter's rotating magnetic field collides with the slower solar wind. It's noisy, it's chaotic, and when most objects pass through it, they show mild turbulence. But 3i Atlas didn't just experience turbulence, it appeared to generate structure within it. A magnetic bubble began forming around the object, symmetrical, steady, and just wide enough to encompass the entire body and a small surrounding shell of dust. In situ, readings from a radio spectrometer on Earth showed polarization changes in reflected emissions, indicating the presence of an aligned magnetic field around Atlas itself. This triggered a question that no one expected to ask. Does 3i Atlas have its own magnetic field? Natural comets don't generate strong magnetic fields. They are cold, passive, and lack the internal dynamo processes that would sustain magnetism. While some plasma interactions can induce temporary magnetic features, these are usually weak, erratic, and quickly collapse. But 3i Atlas was different. The structure forming around it was coherent. It appeared to resist the twisting effects of Jupiter's outer magnetotail and remained stable for over 3 hours, slowly rotating, matching the spin of the object itself. This hinted at an internal organization, or at least a persistent magnetic memory, the kind that only arises in structured materials or engineered systems. Adding to the puzzle, telescopic readings captured from Chile's Cerro Tololo Observatory showed strange polarization angles in the dust cloud surrounding Atlas. These particles weren't drifting randomly, they were aligning, not with the solar wind, but with something closer and stronger, an internal magnetic shell. One possible explanation came from a team of plasma physicists in Japan. They modelled Atlas as a ferromagnetic core encased in a crust of volatile materials. As it passed through Jupiter's plasma sheet, this core could have become energized, reactivating latent magnetic properties and forming a temporary magnetosphere. But this would still require internal structure, and more importantly, a composition unlike anything seen in a typical comet. A more radical theory emerged. Atlas was not reacting to Jupiter's field. It was using it. According to this view, 3i Atlas may have been designed, or evolved, to navigate through magnetic zones, harnessing energy not from light or gravity, but from charged environments. In that sense, the plasma sheet wasn't an obstacle, it was a charging station. After its mass loss, its Doppler shift and the collapse of its anti-tail, this magnetic resurgence looked less like a coincidence and more like a phase. Something had changed inside the object, or perhaps something had activated. Because for the first time in its journey, 3i Atlas didn't just reflect the universe around it, it shaped the space it moved through. In every deep space mission, every cometary analysis, every model of interstellar behavior, there's one rule that always applies. The energy has to come from somewhere. Astronomers call this the energy budget. It's the running balance sheet of how much energy an object receives, how much it emits, and what it uses internally to power motion, heat, pressure, or change. And on the morning of December 7th, the energy budget for 3i Atlas broke. Until this point, most of the object's behavior, although strange, could still be explained by combinations of known physics. Solar heating could explain dust venting. Tidal friction near Jupiter could explain minor internal shifts. Charged particles might account for the magnetic shell. But as observations stacked up, the energy required to explain these features began to outpace what 3i Atlas could realistically absorb from its environment. Let's break that down. After passing Jupiter, the object began exhibiting simultaneous high-energy phenomena: rapid directional acceleration, magnetic field interaction, radio emissions in multiple bands, sudden mass loss with no visible surface venting, a stable trajectory with no tumbling or visible torque. Each of these requires energy, often a lot of it. But 3i Atlas was moving away from the Sun. Its solar intake was declining. It was not near any high radiation zones. There were no external collisions, no nearby moons or gas plumes to feed off. The thermal signature from its core was cooling, and yet the activity increased. By late afternoon on December 7th, the combined data from ALMA, JUICE, VLA, and ground-based optical observatories painted a stunning picture. 3i Atlas was emitting more energy than it was absorbing, not by a small amount, but by a factor that made passive explanation impossible. The math no longer worked. This anomaly had two parts. First, where was the energy coming from? And second, how was it being used? Some experts turned to the idea of residual internal heat, the kind that could be stored inside a dense metallic core or trapped beneath insulating layers of regolith. But that didn't align with the timing. Any internal heat should have radiated most strongly near perihelion, when the sun's heat was at its peak. Instead, the most active emission phase came after that, when the object was cooling. Others floated the possibility of chemical energy. Perhaps 3i Atlas had pockets of volatile compounds that, when triggered, released energy through exothermic reactions. This could explain isolated events, but not the sustained patterned emissions, not the magnetic field stability, and certainly not the Doppler-shifted acceleration. Then, a new hypothesis emerged, one that straddled the line between comet science and spacecraft theory. What if 3i Atlas wasn't drawing power from external energy, but from internal conversion? Some materials, especially in engineered systems, can convert stored mechanical stress into electromagnetic radiation. Others can use shifting magnetic fields to induce electrical current. There's even a class of theoretical constructs in propulsion physics that proposes vacuum energy harvesting from subatomic fluctuations. In the natural world, these are fringe ideas. In controlled systems, they're power sources. But here was the problem. If Atlas was using an internal energy mechanism, it implied control, regulation, a system of storage, release, and directional application. And that broke the final rule. Because in the standard model of comets, there is no system. There's dust, rock, ice, and the chaos of space. Yet 3i Atlas was performing like an engineered platform with an active power budget. The object wasn't just glowing, it was managing energy, distributing it, applying it precisely during vector shifts, magnetic resonance phases, and broadcast intervals. And perhaps most unsettling of all, nothing it was doing made it look weaker. It wasn't burning out, it was ramping up. Whatever was happening inside 3i Atlas was not a slow decay. It was a transition into something new, something with power. It was subtle at first, a flicker, a glint against the void. On the morning of December 7th, just hours after 3i Atlas crossed through Jupiter's outer magnetic region and reactivated its radio emissions, deep sky imaging arrays began noticing something that hadn't been seen in weeks. A reflective flash. Not random, not chaotic, but rhythmic, like a pulse. To those watching closely, it wasn't unfamiliar. In fact, a similar phenomenon had been documented weeks earlier during Atlas's approach to perihelion. Back then, telescopes in the Canary Islands and Chile caught what appeared to be high albedo flashes coming off the object, concentrated at regular intervals, each separated by roughly 38 seconds. Some theorized these were surface glints caused by reflective ice rotating under sunlight. Others thought they were sensor noise or momentary alignment anomalies. But now the same flash had returned. Only this time the object was past Jupiter, outbound, cold, and covered in a dispersing cloud of dust. Any reflective surface should have been buried. Any spin-based glinting should have faded with the coma's growth. Yet here it was, flashing again, this time more precise. The South African Astronomical Observatory, SAAO, recorded a consistent interval of 21 seconds between flashes. Not a perfect pulse, but far too structured to be natural scattering. Moreover, the flashes originated from a consistent point relative to the object's core, as if a specific panel or surface was catching light and flaring it back toward Earth. That made no sense. Natural comets don't have fixed reflectors. Their surfaces are rough, spinning, asymmetrical. If something glints, it does so sporadically, based on how dust reflects off uneven angles. But this flash was repeating, and it was moving. High-resolution photometry revealed that each flash was also slightly Doppler shifted, implying that it wasn't just bouncing sunlight, but emitting or enhancing it in some structured way. This wasn't a flash caused by spinning ice, it was a directed optical return. The timing of this reappearance raised immediate questions. Why now? Why after the radio bursts? Why after the anti-tail dissolved and the object's energy output surged? One possibility was that the surface of 3i Atlas had reconfigured, that the mass loss event exposed a previously hidden reflective layer. But if that were true, the glint would have been irregular and chaotic, at least initially. Instead, the flash came back clean, like something had been waiting for alignment. An even stranger observation came from the Hubble Space Telescope's Outer Solar Tracking Array, which captured brief light curve anomalies in the same time frame. These dips and spikes occurred exactly in sync with the flashes, not before, not after, but on the millisecond. This hinted that the flash wasn't just visible light, but was part of a broader signal event, affecting instruments across the spectrum. At this point, several astrophysicists began connecting the flash to a phenomenon known as retroreflective signaling, a technique used in satellite arrays to bounce light or data precisely back to a known observer. In space engineering, these are used in docking systems, communication relays, and even LIDAR return beacons. The speculation turned uncomfortable. Was 3i Atlas responding to Earth's observation windows? Was the flash a navigational cue, a handshake? And then it got weirder. The final 3 flashes recorded that night didn't reflect solar light at all. They occurred during Jupiter's shadow transit, a period where the sun was completely blocked behind the gas giant. No solar illumination, no background starlight, and yet a flash, which means it wasn't a reflection anymore, it was self-generated. At this stage, there were no more comparisons to normal comet behavior. No ice can glow on command, no dust particle maintains precise timing through magnetic turbulence, and no accidental geometry repeats every 21 seconds through a coma thousands of kilometers wide. This wasn't a flash caused by sunlight, it was a beacon reactivating, brighter, tighter, and seemingly aware of its audience. Whatever was inside 3i Atlas had just turned back on. When tracking celestial bodies, especially comets, astronomers expect a certain logic to their motion. Radiation pressure pushes dust away from the sun. Gravity shapes the arc. Ion tails point directly away from solar wind. Everything flows outward from the energy source, the sun. but 3i Atlas has never followed that logic. Even before it passed perihelion, strange dynamics were recorded in the way its dust cloud moved. Jets fired not towards space, but inward, sideways, even, inexplicably, sunward. These were dismissed as unstable venting patterns or as the result of a tumbling asymmetric core. But as of December 7th, those patterns had returned, and they were no longer ignorable. Observatories across 3 continents, using both visible light telescopes and L-band radar, confirmed that despite the object's outbound trajectory, small but measurable components of its motion were resisting solar influence. Instead of trailing behind, several thin dust streams and gas plumes were coalescing opposite the expected vectors, moving in an anti-solar direction. In other words, 3i Atlas was subtly moving against the Sun. Now, it's important to clarify, this wasn't a full reversal. The object itself was still following a path away from the solar system. But portions of its emission, its dust, its radiation, and possibly even micro-movements of its core were resisting that path. This is something we've never seen before in a deep space object of this type. Normal comets shed material passively, and solar radiation dictates where that material goes. But with Atlas, some of the particulate matter wasn't drifting, it was holding position. In some regions, it was even accelerating against the Sun's influence. The SOHO spacecraft provided some of the clearest imaging yet. High-contrast composites of the object's surrounding envelope revealed a bow shape, not behind the object, but in front, as if the debris wasn't being left behind but guiding the way. Then came another surprise. By midday, polarization analysis from the Very Large Telescope, VLT, in Chile, indicated that the antisolar emissions weren't simple outgassing, they were magnetically aligned. Not with the Sun's heliospheric current sheet, but with the magnetic structure surrounding Atlas itself, which, as we now know, had been strengthening since the Jupiter transit. This hinted at control, not in the science fiction sense, but in the sense that motion wasn't happening by accident. The vectors of the material weren't chaotic, they were converging, aligning, and, most critically, not being carried by solar wind. They were defying it. This persistence of antisolar motion suggested one of 2 things. Option 1. Atlas has an internal propulsion mechanism. This would allow it to actively control which direction its emissions move, not just as a result of pressure or heat, but as a choice. That's highly controversial, and currently unsupported by any cometry model. Option 2. Atlas is using its own electromagnetic field to shape how material leaves its surface. In essence, it's using magneto-hydrodynamic principles, channeling plasma or dust in a way similar to how solar sails or artificial ion drives operate. Either way, this isn't passive behavior. This is intentional vector shaping, and it means that 3i Atlas is not just moving through space, it's navigating it. Why does that matter? Because if an object this far out, this cold, this distant, this seemingly inert, is still maintaining anti-solar emissions, then it means its internal systems have not just survived their solar encounter, they've adapted to it, they're persisting. The Sun should have stripped the object clean, should have pushed everything outward, should have left behind nothing but a cooling shell, but instead, Atlas is now forming structure in opposition to the Sun itself, and that means its next moves will not be shaped by physics alone, but by whatever intelligence or mechanism is driving this resistance. At first, it looked like a sensor glitch. In the early hours of December 7th, as global observatories continued to track the strange behaviours of 3i Atlas, a peculiar reading appeared on the frames captured by a deep-field telescope array in Western Australia. Positioned a few degrees off the primary body of Atlas, a faint, consistent dot had emerged, barely distinguishable from the surrounding stars. But it wasn't a star. It moved, and not randomly. It was matching the trajectory of 3i Atlas almost exactly. Not ahead of it, not far behind, but locked into a trailing pattern at a distance of just under 1/10 of a degree of arc. On closer inspection, it maintained velocity within a margin too narrow for coincidence. In simple terms, the object was shadowing Atlas. This led to an immediate question across the astronomical community. Was there a second object all along? This wasn't the first time such a possibility had been floated. Early in Atlas's detection arc, when it first began exhibiting anomalies in light curve and reflectivity, a few outlier scientists suggested the object might not be singular, but a binary pair or even part of a structured cluster. Back then there was no evidence. Everything pointed to one core, one coma, one tail. But now the data told a different story. The faint object appeared intermittently on instruments that were sensitive to near-infrared and shortwave radio. It pulsed with its own weak signature, not reflective, but active, emitting a low-level electromagnetic signal that was consistent in rhythm but not in intensity. At times, it dimmed entirely, invisible for minutes or hours, only to reappear exactly where it should be, as if it had never moved. More puzzling was its orientation. The secondary object didn't tumble. It held a fixed face toward 3i Atlas. Over the span of several hours it appeared to be watching, or tracking, the main body, almost like a drone following a mothership, close, silent, and always aligned. Some hypothesized that this second object could be a fragment, a chunk that broke off during the recent mass loss event and had become gravitationally or magnetically tethered. But that didn't explain its coherence. It wasn't diffusing or spinning chaotically. It wasn't venting dust or trailing a tail. It was stable. Others believed it might be a natural companion, like a binary asteroid system, where two bodies orbit a common center of mass. But there was no orbital wobble, no center point between them. The secondary object remained in a passive pursuit formation, like something built to follow. One of the most intriguing clues came from the SOHO spacecraft, which captured a brief anomaly in the object's projected path, a shadow dip that wasn't consistent with any known debris or background distortion. Analysts compared this with Earth-based L-band radar returns and found a subtle delay echo in transmissions that passed through Atlas's wake. That echo matched the estimated location of the secondary object, and it showed structure, not a perfect sphere, not a jagged rock, but something elongated, angular, with a reflectivity curve that looked nothing like dust or stone, a shape that reflected like metal. At this point, no one in the mainstream astronomical community was ready to declare this a probe, a craft, or a secondary vehicle. But even conservative models began adjusting to a new term, accompanying body. Because whatever this was, it wasn't falling away, it wasn't being left behind, it was sticking with Atlas, perfectly, silently, and on purpose. And the real question wasn't just what this second object was made of, it was why it was there at all. For most celestial bodies, especially ones that pass near the Sun and endure intense gravitational interactions, rotation is one of the first things to change. Tidal forces stretch, torque, and sometimes tumble comets and asteroids into chaotic spin states. But with 3i Atlas, a different story is unfolding, one that has left scientists genuinely stunned. Its internal rotation hasn't changed at all. On the morning of December 7th, multiple observatories completed rotational analysis of Atlas based on light curve variation, polarimetric mapping, and radar pulse. Reflection data gathered before, during, and after its interaction with Jupiter's magnetic sphere. The conclusion, its core rotation period, the time it takes for the object to spin once around its own axis, had not shifted in any measurable way since its initial detection. That shouldn't be possible. Let's consider what 3i Atlas has been through. It passed near the Sun, shed mass in high volumes, encountered enormous tidal forces, and just days ago released a significant quantity of dust and gas, some of which reversed direction against solar pressure. Any of those events alone would be expected to alter a comet's rotation. Even a minor venting asymmetry can produce enough thrust to slow or speed up spin over time, but Atlas stayed locked, no slowdown, no speed up, no precession. Its rotation appears not only stable, it's regulated, and that word, regulated, is where the conversation takes a strange turn. The internal rotation of comets is generally chaotic. Many spin erratically, wobble unpredictably, or even enter tumbling phases. They're irregularly shaped, their mass is unevenly distributed, and their surface activity is uncontrolled. Their spin reflects that disorder. But 3i Atlas is different. Its light curve reveals a harmonic pulse, a clean, repeating pattern in brightness that has remained consistent for weeks. It's not just spinning, it's pulsing in a pattern that matches its rotational axis perfectly. That precision suggests balance. Balance suggests symmetry. And symmetry at this scale suggests internal structure. Radar scans taken from Earth's southern hemisphere provided another layer to the mystery. When pulses bounced off the object's surface and returned, they showed minimal scattering and high surface coherence, as if the internal body was composed of consistent material layers or was reinforced. And still, the most confounding evidence came from Atlas's response to external forces. It wasn't affected by Jupiter's pull. It didn't tumble after releasing material. It didn't wobble as it passed through the solar wake. Its orientation held true, not only with regard to its own spin axis, but to its trajectory vector. That's not just stable, that's intelligent-seeming stability. In response, a few researchers quietly began modelling Atlas's behaviour, not as a natural comet, but as a gyroscopic platform, a structure designed to remain rotationally fixed regardless of external influence. These systems are common in satellites and deep space probes. They allow for precise orientation of sensors, antennas, or propulsion systems, but they're not supposed to exist in nature. Yet that's the only thing that makes sense here, because even if we assume Atlas has an unusually dense or symmetrical core, the lack of any angular deviation during mass loss is beyond probability. Something inside this object is keeping its spin rate constant, with no measurable drift. If it is artificial, even partially, then we may be witnessing one of the oldest forms of cosmic design, rotational control as a stabilizing foundation. And if it's natural, then it is nature repeating a pattern we thought only intelligent beings had mastered, using spin not just for motion but for orientation, alignment, and possibly for communication. Because Atlas hasn't just held its rotation, it's using it. It began with a flicker, soft, internal, almost biological in appearance. On the morning of December 7th, just hours after the secondary object was confirmed, and Atlas's rotation was found to be unnervingly stable, a new phenomenon emerged, a glow from within the core itself. This wasn't a surface flare or a sunlit reflection, it was internal. Multiple ground-based infrared telescopes, including the Keck Observatory in Hawaii and the Gran Telescopio Canarias, independently reported a strange mid-infrared spike coming directly from the center of 3I Atlas. The glow was subtle, not bright enough to trigger automatic tracking alerts, but it was consistent. More importantly, it didn't match the profile of a surface activity, solar heating, or residual venting. The emission originated from inside the core, from a region that should, by all known physics, be cooling rapidly after shedding mass. But instead of fading into the cold void beyond Jupiter, Atlas had started warming up from within. Spectral readings showed a narrow band of emission centered around a frequency typically associated with low-energy plasma discharge, the kind seen in ionized gases under pressure. That alone raised questions. How could a deep space object with no internal reactor, no sunlight exposure, and no obvious chemical source emit such a specific glow from inside? Some scientists theorized the core might be filled with highly pressurized volatiles, materials like ammonia or methane trapped in deep ice pockets. If those began to sublimate in isolation, it could create momentary heat, but that didn't explain the duration. The glow held steady for over 3 hours, far longer than any chemical venting cycle observed in natural comets. Then came the real surprise. Using backscatter data from the Very Long Baseline Array, VLBA, a collection of linked radio telescopes spread across the globe, researchers generated a crude internal map of the object's density. What they found didn't resemble a solid mass. Instead, the core appeared partially hollow, with an energy-emitting region suspended at its center, as if something was contained inside. A hollow structure is not unheard of in nature. Some asteroids and comets are riddled with voids from past collisions, but those voids don't glow. This one did. And its emission pulsed faintly, with a rhythm not unlike the reflective flash recorded earlier. The pulses were in sync, not random, not decaying. This suggested a connection between what was reflecting outside and what was activating inside. Then, at precisely 4:11 UTC, a new signal emerged, a low-frequency hum riding on the edges of the infrared band. Not a sound, but a patterned wave, modulating in intensity every 30 seconds. This modulation was detected by instruments in both hemispheres and cross-confirmed using side-looking radar from ESA's Deep Space Network. What caused it? No one knows. Some speculated a natural oscillation, a kind of internal resonance due to thermal imbalance. But that doesn't hold up under scrutiny, because resonance decays. This wave held, The glow held. The object remained awake. At this stage, the term core no longer feels appropriate. What we are observing inside Atlas is not a cold remnant. It's not a dust-filled void. It is a compartment, a self-contained region emitting directed energy at precise intervals, apparently unaffected by the surrounding space. And now, the implications deepen. Because this internal glow, paired with the object's unchanging rotation and symmetrical flash returns, suggests we're no longer looking at a passive interstellar rock. We are watching something turn itself on from the inside out. And for the first time, Earth-based sensors are detecting not just motion or mass, but intent. On the morning of December 7th, something changed. Not in the skies, but in the way agencies responded to what was happening up there. For weeks, the European Space Agency had been one of the most active institutions sharing observational data on 3I Atlas. Their Solar System and Planetary Monitoring Division had published near-daily bulletins tracking everything from orbital updates to magnetospheric interactions. Their early detection of dust asymmetry had helped prompt global interest in the object. Their radar archives gave insight into Atlas's unexpected mass loss. But suddenly, that stream stopped. Without warning, ESA's live tracker went into a suspended state. The daily logs that had once provided detailed positional updates now displayed only a static timestamp. Last update, 6:14 UTC, December 7th. Subsequent refreshes failed. Access logs showed quiet removal of image assets, while the press portal displayed a brief vague message. Observational data under internal review. Updates will resume pending evaluation. That language was unusual, not temporary system error, not maintenance. It was intentional, and vague enough to raise alarms. Within hours, amateur observers and data analysts began cross-referencing archived snapshots of the ESA tracker with newly released positioning data from NASA and JAXA. What they found didn't align. ESA's last orbital path calculation placed Atlas on a gently decaying outbound arc, but the new readings showed a slight but undeniable trajectory shift, enough to potentially affect long-range projections. And then came the blackout. ESA's internal observation logs, normally mirrored by third-party repositories, stopped syncing. Automated tools that scraped ESA's feed were met with 403 errors. Even public datasets used by educational platforms were replaced with placeholder variables. To outside experts, this wasn't just data maintenance, it was containment. Why would ESA halt updates now, just as the object's behavior was becoming the most anomalous? Why, when so much of the world was finally watching, would they choose this moment to go dark? Some offered cautious technical explanations, that the mass loss event had destabilized data integrity, that they were simply recalibrating models, or waiting for coordinated confirmation from their partners. But others, quietly, began saying what no official would. ESA saw something they weren't prepared to explain. One possibility was the hollow core glow. Another, the silent trailing object identified just hours before. But perhaps the most uncomfortable truth was simpler, that the data no longer matched the models, and ESA could no longer publicly justify the assumptions they had been making since the beginning. To support this theory, one only needed to look at the internal correspondence leaked later that same day. Though not formally confirmed, a screenshot circulated from a private Slack channel tied to ESA's astrodynamics lab. It contained a single line. "We're not publishing orbital deltas without confirmation. This can't just be drift. Someone needs to say it." Within hours, the post was scrubbed, accounts deactivated, no public comment followed, but the damage was done. The silence from ESA created a vacuum, one that was quickly filled with speculation, unofficial tracking maps, and community-led triangulations. Some claimed that ESA had passed jurisdiction to NATO. Others insisted the European Commission had invoked emergency oversight for strategic space assets. No theory could be verified. But the pattern was clear. Transparency had ended. Whatever 3I Atlas had done near Jupiter, whatever it was doing now, had reached a point where even the most open science agencies were retreating behind closed doors. The question was no longer what ESA saw, it was why they felt the need to hide it. At first, the signs looked like collapse, a mass loss event, a dissolving anti-tail, a hollow core leaking energy from within. But as each new anomaly emerged, a quiet realization began to spread among a small group of observers. What if this wasn't breakdown? What if it was preparation? The question is simple and terrifying. What if 3i Atlas isn't winding down, but winding up? It's not the first time space researchers have reversed their assumptions about what an object's instability might mean. Supernovae, for example, were once thought to be simple deaths of stars. We now know they can be transitions, gateways to black holes, neutron stars, or even something stranger. Cosmic shedding is not always the end of a story. Sometimes it's the beginning of something new. And 3i Atlas? It's acting like something about to move. Let's start with its orientation. Since the mass loss event, Atlas has not tumbled or altered its spin, a feat nearly impossible for an object that just expelled significant material. Instead, it remains rotationally locked, pulsing with a perfectly rhythmic light curve. This is behavior we associate with controlled systems, not natural ice and rock. Then there's the hollow core. Infrared and radar scans show a compartmentalized cavity, one that now glows from within, emitting structured pulses of heat and low-frequency radiation. If this would collapse, we'd expect decay. Random fluctuations, irregular heat dispersion, but instead we see uniformity, a system stabilizing itself, as if gearing up for something. And most notably, the object's mass is decreasing, but its trajectory is refining, not degrading, not wobbling off course. The course is tightening, sharpening into something deliberate. ESA's final, unconfirmed orbital delta, captured just before their feed went dark, suggested a minor but measurable vector shift. It wasn't random, it was aimed. If we look at historical spacecraft behavior, particularly interstellar probes like Voyager and New Horizons, we find eerie parallels. Prior to gravity assists, these missions go through power cycles, stabilization checks, orientation locks, final telemetry bursts. The behavior is all about readiness, all about departure. And now some experts are whispering, is that what we're seeing with Atlas? The anti-tail that's fading? It may not be fading, it may be retracting. Event closing. The glow, an ignition protocol, the electromagnetic pulses, signaling loops, either to the companion object trailing behind or to systems we haven't even detected yet. Here's the speculative model. Atlas is not the mission. Atlas is the launch stage, a shell, a carrier, a vehicle that was never meant to complete the journey, but to deliver something. Something that now prepares to move independently, or disappear completely. The recent observations of a stable secondary object, one shadowing Atlas's path, may support this. That faint companion may not be following, it may be waiting. Because if Atlas is a delivery platform, then we may be witnessing its final preparations before release, before departure, before a maneuver that doesn't just mark a shift in motion, but a shift in purpose. None of this is confirmed, but all of it is grounded in real data. And more importantly, nothing natural about Atlas's behavior explains the synchronization, the stabilization, the internal ignition signatures, or the orbital correction that defies basic physics after a mass loss event. What we're left with is a chilling possibility. Atlas isn't dying, it's activating. And if that's true, then the object that humanity first spotted as a wandering rock from another star may not be lost. Matter, but the start of something intelligent. Something whose first true movement is still to come. For days it held firm, despite shedding material, despite glowing from within, despite pulsing with symmetrical flashes and releasing patterned emissions from its hollow core. 3i Atlas never wavered. Its path through space was calculable, smooth, and consistent. Until now. On the morning of December 7th, the silence broke. Independent observatories in Chile, Australia, and Japan all detected a subtle but undeniable deviation in Atlas's trajectory. Not dramatic, not chaotic, but intentional looking. The object wasn't drifting, it had adjusted. It's the kind of change that's only visible to high-precision tracking systems, a vector shift measured in microradians. But across interplanetary distances, even the smallest angular deviation can translate into a completely different destination, or intention. And that's exactly what's alarming the scientific community right now. Until this point, every projected model had Atlas continuing on a steady outbound path. After passing Jupiter, the expectation was that it would begin to slow, gradually drift further from the Sun, and eventually exit the solar system entirely, assuming its velocity held. But that's not what's happening anymore. Instead of accelerating outward or maintaining inertial drift, Atlas made a course correction, a redirection, a deviation toward something. The new vector angles it ever so slightly inward, not back toward the Sun, but toward a region of space where no significant gravitational body exists to explain the motion. No planet, no moon, no known cometary attractor, nothing. Which leaves only two possibilities. Either Atlas was pulled by something we don't yet see, or Atlas pushed itself. Let's explore both. If this was gravitational, some unseen mass disturbing the object's flight path, we would expect surrounding dust and background stellar light to show signs of lensing or distortion, but no such signatures have been detected. The space it moved into is, by all known measurements, empty. If it was mechanical, a push, then it must have come from within. And here, the pattern gets even stranger. Exactly 43 minutes before the trajectory shifted, a spike in mid-infrared radiation was recorded from Atlas's core. The internal glow that had been pulsing with subtle rhythm suddenly surged in amplitude, almost as if a dormant process had activated. Minutes later, the glow faded, and the object's course changed. This timing is impossible to ignore. It's the kind of sequence we'd expect from a propulsion event: energy buildup, release, vector shift. Not unlike a burn maneuver used by satellites when transitioning between orbits, only this wasn't a satellite, and the mass loss event days earlier. It may not have been an accident. It might have been fuel staging, shedding unnecessary exterior material before, initiating a controlled movement. Or it could have been the final decompression before a secondary engine, or pressure-based ejection system, activated deep within the hollow structure. Regardless of method, the result is now visible across every major tracking system. 3i Atlas has left its projected flight corridor. NASA's Deep Space Network has already reclassified the object's status. Instead of interstellar outbound object, it now appears under the tag Active Anomaly. ESA remains silent. JAXA's last telemetry echo failed to lock on, and private observatories are scrambling to update their tracking protocols. Because when a cosmic body suddenly moves with precision, we have to ask, who's in control? And if 3i Atlas isn't a comet but something capable of fine-tuning its own motion in deep space, even slightly, then this isn't the end of its journey. It's a correction. The kind of correction made by something that knows where it wants to go. And that's no longer just a question for astronomy. That's a question for every agency that's been watching, and now, clearly, choosing silence over explanation.